So before going on to talk about disaccharides and polysaccharides, I want to go back and review, stress something from the last video. All right, and that's to mention a little bit of the vocabulary of what's considered the anomeric carbon. All right, so we talked about the fact that there's a certain hydroxyl that could either be in its down orientation or its up orientation, and that was always the hydroxyl that's on this carbon right next to the oxygen that's in the ring. All right, and that's what's called the anomeric carbon. All right, and the reason that it's called the anomeric carbon is that because of that, you either have glucose in this variety or in this form right here, and the relationship between these types of molecules are considered anomers of each other. All right, so in an organic chemistry sense, you would say that these two are diastereomers of each other, because they're molecules that contain a bunch of chiral centers, and they're not mirror images of each other. All right, and so, but like all the groups are attached to the same carbons, but they're not mirror images. So that makes them diastereomers. But when you're talking about saccharides specifically, the term that gets used is anomers. Another thing that I wanted to mention is that once you identify that anomeric carbon, which in this case would be this carbon right here, that is considered to be the number one carbon of the monosaccharide. So the numbering of this goes 1, 2, 3, 4, 5, 6. All right, and that numbering is going to be important when we start to talk about the linkages between monosaccharides. All right, one last thing I wanted to point out is there's actually two carbons that are neighboring this oxygen in the ring. So why is this one right here considered the anomeric carbon? Well, notice that there's not a hydroxyl on this carbon right here. All right, so there's a hydrogen, there's this group, and then there's a bond going down here. But only one of the neighboring carbons is going to have that hydroxyl. So that's how you identify the anomeric carbon. All right, and remember, one of the things that makes that anomeric carbon special is when this thing opens back up to its linear form, that anomeric carbon is the one that would either be the aldehyde carbon or the ketone carbon. All right. Okay, and so while there are a lot of examples of monosaccharides out there, generally what you're going to find in carbohydrate chemistry is that monosaccharides are going to want to link to each other to create either disaccharides, trisaccharides, or if you link enough of them together, you generally call it a polysaccharide. All right, and starch is a good example of a polysaccharide. All right, so what I've done here is I've shown two common monosaccharides side by side. This is beta-galactose, this is beta-glucose. All right, and you'll notice that there's two hydroxyl groups that are close to each other. And these guys right here are going to get linked together in what's called a condensation reaction. All right, and the reason it's called a condensation reaction is that when these join, it's going to get rid of a water molecule. All right, so when these guys join together, you'll notice there's just one single oxygen atom that connect the two rings, whereas before there were two OHs. All right, so somewhere we've lost an H from one and an OH from the other. All right, so that's why we call it condensation. We've lost a water molecule. All right, so when these guys are joined together, this is now considered a disaccharide. So this particular disaccharide right here is lactose, which you might have heard of. You commonly think of milk when you think of lactose. It's the sugar that's in milk. All right, so one other thing I wanted to mention, the linkage that connects the two monosaccharides is what's called a glycosidic bond. All right, and specifically the glycosidic bond is going to be the bond between the oxygen and the anomeric carbon of one of the monosaccharides. So you might look at this and say, well, either of these is an oxygen carbon bond. All right, this is oxygen carbon, this is oxygen carbon. So what is so special about this one right here? All right, so remember, this is the anomeric carbon right here. And the chemistry of this makes this this is going to be a less stable molecule. Right? So, for example, if we were to break this molecule apart, this oxygen would go with this monosaccharide right here. All right, because this bond right here is a much stronger bond than is this one right here. So you'll notice that when I drew this version of lactose right here, I drew these as the chair conformations. And the reason for drawing chair conformations is it gives a better three-dimensional sense of the molecule. All right, and generally this front edge right here is bolded a little bit more to give you that sense of this one is the side that's closer to you. All right, so you get a pretty good three-dimensional sense of how these atoms, these bonds would orient themselves in space. All right, the problem is that it's a lot more cumbersome to draw things in the chair conformation as compared to the Hayworth conformations. All right, so chemists more commonly will draw these in a Hayworth conformation, but in a way that shows the way that the monosaccharides are connected to each other. All right, so notice that in this chair conformation, you can see that this bond is in the up direction. All right, and the way you do that, there's actually two ways that you can do this. One is like this, where we have, this is your galactose monosaccharide right here, and notice that this bond is going up in the same way that this bond right here is going up from the ring. All right, but notice from the 4 carbon of the glucose, the bond is coming down. All right, and that's why we show it coming down like this. All right, and this is the convention that I've noticed that the IB curriculum more commonly uses. All right, I do want to point out though that there's another convention for how these are drawn. All right, and so that convention looks something like this. All right, and it can be a little confusing when you first look at it. All right, so the point that we want to get across is that this bond, this oxygen is above the plane of this ring right here, but it's below the plane of this ring right here. All right, and if you're going to do that in a spatially correct way and draw that, you'll notice that this monosaccharide is on a different level than this monosaccharide right here. And if we had to do the same thing again, we'd have to draw a monosaccharide up here. And so you can end up getting it's hard to draw a lot of these side by side because it just takes up a lot of vertical space when you do that. All right, so there's a little shortcut that allows you to get around that. All right, and that's what I'm showing right here, is where I want to show this bond from this carbon to this oxygen goes up. All right, so what I'm going to do is I'm going to show something going up, but then I'm going to do this little zigzag right here down to an oxygen. Here I want to show the bond going down from this monosaccharide. So I'm showing this going down from this monosaccharide right here, and then I'm showing this zigzag going back up to the oxygen. All right, and the reason for doing this is that if I have to draw a lot of these in a row, I can draw all of these monosaccharides at the same level on the piece of paper. All right, so the one thing that can be a little bit confusing about this is you actually end up having an intersection of line segments. All right, and normally that means a carbon atom exists there. All right, so you just need to realize that when you're doing this, these do not represent carbon atoms. They're just a way to represent the direction that the carbon-oxygen bonds come from the monosaccharides, but it's done in a way so that you can draw them side by side. All right, so another common example of a disaccharide is sucrose, all right, which is commonly table sugar. All right, and sucrose is made up of 2 monosaccharides, glucose and fructose. And I want to point out that I made a mistake here. There should be an OH going down here, but there should be an OH going up here. All right, so I omitted 2 of the hydroxyl groups. Same thing over here, a down OH over here and an up OH over here. All right, so when these guys get, when the condensation reaction occurs that joins these, you end up getting this stereochemistry. So this bond right here is going to be below the plane. All right, so you'd have a hydrogen which is above the plane. All right, and on this one, that carbon-oxygen bond is below the plane as well. All right, so notice that it's opposite of this one right here. So here, this was going up above the plane. Here, it's going down below the plane. All right, so there's also, just like we had this little shortcut right here, There's another way of doing that with this type of a drawing, which is when you draw, you go down and you draw a little right angle to an oxygen, and then you draw another right angle and you come up. All right, so notice either way you draw this, you can tell that the linkages are in the down orientation. All right, you just need to realize that this little intersection of line segments right here would not be considered a carbon. All right. Okay, so one other thing I wanted to mention about sucrose. Sucrose is somewhat of a unique disaccharide. All right, and the reason for that is most disaccharides involve a linkage between the anomeric carbon of one of the monosaccharides and a non-anomeric carbon of the other. All right, so notice this carbon right here. This is not the anomeric carbon of glucose. This right here is the anomeric carbon of glucose. All right, this right here is the anomeric carbon of galactose. All right, so this linkage is between the 4 carbon of glucose and the anomeric, or the 1 carbon of galactose. All right. However, when you're linking glucose and fructose to make sucrose, all right, you'll notice that this right here, this is the anomeric carbon of glucose. All right, it's the one next. It's the one that would have. If this was a hydroxyl right here, this would be the hydroxyl on the carbon right next to that oxygen. All right, on fructose, notice this right here. This would be, if this were a hydroxyl off of fructose right here, it would be a hydroxyl right off the carbon next to that oxygen. So this is the anomeric carbon of the fructose. All right, and so the linkage is between 2 anomeric carbons on neighboring monosaccharides, which is very unique, and it's actually what leads to the stability of sucrose. All right, but keep in mind that is a relative rarity when it comes to polysaccharides.